Oh, hello, this is my second video. So in this video, I'm gonna show some more tricks and with regard to titration questions, problems, and also use the trick or tip I showed in the last video to solve some questions on this A4 paper. There are 10 questions on this A4 paper, all the way to 10. So I'm gonna use my fastest speed with the tip and trick I show. So for first one, when we say the equivalence point, with a weak acid, strong base, or strong acid, weak base, we look at it conjugate acid or base. First of all, if it's a weak base, weak acid and a strong base, we're gonna create a conjugate base. So it's gonna be OBr negative minus and ion. So once we know it's a conjugate base, we're gonna use a formula. So we're gonna do log, and then parentheses. Inside parentheses, use a square root. And we're using a mathematical method to solve this, which is much faster than you do ice table. So for this one, negative log and the parentheses, and you have that chi-square root over there, right? Inside this chi-square root, what do we need? Because we have a conjugate base, so we're gonna put a kb here. We're gonna multiply kb, which is multiplication, and we wanted the molarity of the OBr negative. We want the molarity of it. How do we get the molarity of it? First, we need to know the volume. Second, we need to know the mole. So mole, how do we know the mole? One HOBr create one OBr. In the reaction, HOBr reacts with NaOH. So whatever the mole, remember, at equivalence point, whatever the mole we have for the weak acid, gonna all turn into the mole of its conjugate base. So we calculate the mole with this two number. After we calculate the mole, we need to know the volume that we use for the NaOH. Again, stoic chemistry, that NHOBr is 1-to-1 ratio to the strong base. So whatever the mole we use, also the mole for the base. So the mole we use for the weak acid will not only be the same mole for its conjugate base, but also for the same mole, the strong base we used. So we calculate the mole, very important. Then this is a m here, is a missing m. This is a molarity. We can calculate the volume and use that volume, add on the initial volume, we get the total volume. Then we get the molarity of our conjugate base. So that's all we need to know. Conjugate base, because we're given Ka, we can get a Kb. Once we know the molarity of the conjugate base, this question is solved. So all we have to do is use a calculator here. We use 0.0259 multiplied 0.223. Remember, we need to use this liter. If it's milliliter, we need to change to milliliter. So that's the mole. Mole is 0.00578 mole. So that amount of mole, not only for it's equivalent to the mole of our conjugate base, but also the mole we use with the strong base, NaOH. So that mole gonna divide this molarity, get the volume for the NaOH. That's gonna be approximate. So this number 0.00578 divide 0.131, which is 0.0441. That is our volume for a strong base. Then the volume of strong base plus the volume of our weak acid, then total volume, what we have is 0.0441 plus 0.0259, which equal to 0.07. So the total volume is 0.07 liter. Of course, you make it a 3 significant number. And then now we know how to calculate the molarity of OBr negative. And that's going to be approximate. Very easy, just a simple division. So we're going to do 0.00578 divide 0.07, which is 0.0826 molarity. Now just use this mathematical formula right here, and we can get the final answer. How? Because this is Kb, all right, we use Ka to calculate Kb, then we multiply some molarity, put that a square root, and put a negative log on top, and that's it. So let's do it. So 0.0, put a 826 multiplies. Remember, we want to know the Ka. Right now, Kb, when we have Ka, how do you get a Kb with Ka? 1 multiplies 10 to the negative 14, divide at 25 Celsius. It's 1 multiplies 10 to the negative 14. And divide our Ka, 2.5 multiplies 10 to the negative 9. And then we put a square root on it. That's the molarity of hydroxide ion. After it, at the equivalence point, we have hydroxide ion in the solution generated by our conjugate base. That's the molarity of hydroxide ion. So this molarity, compared with our molarity here, 0.0826, we can see it's very small, less than 5%. Therefore, the small approximation is valid. Therefore, this formula can be used, this mathematical formula. So next, what we do is use negative log and plus answer in it, put answer in it. We got 3.24. Okay, stop here. 3.24, that's POH. So got 3.24 as POH. What's the question asking? It's pH at 25 Celsius. 14 minus 3.24 is equal to 10.76. That's our final answer for this first question. So the equivalence point question is, we have this formula. I'm going to do the same thing. The second question also equivalence point question. So this is a mathematical formula we're going to use for the second question. And again, the very first step is look at is a strong base, weak acid, or strong acid, or weak base. This one is a weak base, strong acid. You're going to generate at equivalence point. You're going to what are you going to have the solution? You're going to have a conjugate acid. Remember this conjugate base is going to have only conjugate acid at the equivalence point. Conjugate acid is going to be acid, NH4 cation. So all right, if it's acid, so we use Ka in this formula. We're given the Kb, we need to turn that Kb into a Ka. Okay, that's the tricky part of this question. Ask you. We turn it Ka. Once we turn it Ka, we need to know the concentration of our conjugate acid here. Okay, how do we do that? So again, same thing. Everything is a 1-to-1 ratio, stoichiometry chemistry, and if you write down that reaction is 1-to-1 ratio, the total mole of our strong acid is going to be total mole of our weak base. Also, the total mole generated, the weak base is conjugate acid. So again, same thing. We're going to calculate the mole for that one. Again, our calculator is here. 0.158 multiplies, remember we need a liter. 0.0232. All right, that's the mole, which is 0.00367. That's mole of our conjugate acid. And then we need the total volume. How do we do total volume? Again, we know the mole for our strong acid, which is equivalent to the weak base mole. So that we're going to do is 0.0232 multiplies 0.185, and then we divide 0.111. That's molarity. Then we got the volume 0.0330. Okay, 0.0330. Let's calculate again because I didn't memorize the number, but it's good to write it down, the number. But usually I can memorize, I missed it. 232 multiplies 0.185 and divide 0.111. And that's 0.0330. I was right, 0.0330. And that's the volume we use for strong acid. And we need to add the weak base volume right over there. So we need to add 0.0232. So the total volume is 0.0562 liter. And then we get the molarity for this conjugate acid. So use 0.00367 to divide 0.0562. That is 0.0653. Okay, that's the molarity. Once we have molarity, we can use Kb to calculate Ka. We put in this formula, we get our result. This one's easier. We don't have to use the 14 to minus it because whatever we got is going to be pH instead of POH. This is conjugate acid. So what we do is here is very easy. So we do first of all we do this two multiplication, and we use again at 25 Celsius is 10 to the negative 14 right here. When you put it in the middle, and we want to divide our Kb that it put there to trick us. We want to get a Ka, so negative 5. Okay, negative 5. That's our Kb. Once our Kb, we multiply our conjugate acid because we are weak base got conjugate acid at the equivalence point. So that is 0.0653. Okay, then we'll put a square on. That is the hydronium ion concentration. You can see how small it is. And if we use it compared with our molarity over here, the conjugate acid and the molarity, it's less than 5%. So go ahead and use this formula. This formula depending on the x, the x is small x assumption. So now we just put a negative log on the answer, and there we are, 5.22. That's our final answer. We use a different color. So it's going to be 5.22. That's it. We solved the second question. So by using mathematical method, there's a mathematical method. Let me circle this one. So this is our trick for this kind of question. So let's jump to question 6, since question 6 closely related to our last video. Okay, let me put it straight. So question 6, and we see that's a standard titration question. We'll have a strong acid and strong base. So strong acid, strong base question. All right. So it's a different solution. So again, whether it's strong acid, strong base, and weak acid, weak base, and strong acid, strong base, and strong base, strong acid, we compare the mole of acid and the base because they're going to react. Historic chemistry reaction. Then we'll find out which one is more, which one's less, which one's an excessive reactant, which one's not. So first step is like we'll calculate a mole for each. This one, we got these two numbers together. So let's do it. Here's the calculator. And we do 0.1 multiplies 0.16. That is 0.06. Okay, let's put it here. So that's a mole of, say, HCl4. That's strong acid. And that's, you need to memorize. That's strong acid. If you don't memorize a list of strong acid and base, you're going to have a hard time to do this kind of questions. So HClO4, that's a 0.016 mole. Before the reaction starts, that's the number of mole. And then let's calculate lithium hydroxide, which is 0.23 multiplies 0.03. That is, okay, 0.0069 mole. And I've got to have lithium hydroxide over there. And now we know that we're going to have acid, strong acid left. Okay, when we have a strong acid left, we'll have a mole left, right? We need a concentration. So the trick of this one is the mathematical formula for this one is just a negative log. Since it's just the acid, we don't need to use 14 to minus it. It's just the concentration of whatever left for the strong acid. And that's it. That's your pH. So now we use the first number minus second number. We're going to get the mole for the strong acid. For the total volume, we don't have to calculate it. It's already there. 100 multiplies 30. So that's quite straightforward. How do we do this? All right, let's do this. 0.016 minus 0.0069, that's equal to 0.0091. So remember, when we do plus and a minus, a significant number going to be the least number after the dot. So that's going to be 3. So we're going to have 0.009 mole. That's whatever left for our strong acid. And for our total volume, going to be 100 plus 30. That's 0.13 liter. So mole divide liter. 0.009 divide our liter 0.13. And that is 0.0692. 0.0692. And that's it. That's the molarity of our strong acid. And strong acid, we use that mathematical formula. So negative log 0.0692. And we got our pH 1.16. 1.16. That's solved. Question 6. Question 7, same kind of a question. Okay, but here's a twist. Determine the pH before addition of the strong acid. So originally it's a weak base. And this question, we use this formula. It's just a weak base. So formula gonna be same thing, log. Okay, we need to use 14 to minus the result because this is the base. So we're gonna do Kb over here, and we need a concentration of NH3. I've already given the concentration, which is 0.14. So this is one is straightforward. Don't need any additional calculation. Just use the formula, we can get the result. So what we do is use a negative log, and let's do from inside to outside. So 0.14. That's what is that? That's the molarity of our weak base. Multiplies, and it's Kb, 1.8, 10 to the negative 5, and that's it. And then we'll use square root. That's how much hydroxide ions in. Sorry, I didn't show my calculator here. That's how much hydroxide ion concentration is. And we'll compare that concentration with 0.14. It's much less than 5%. Therefore, the formula is usable. And what we next to do is put a log on it, on the answer. And that's it, 2.799. So that's going to be 2.80. So this one is 2.80. It's going to 14 minus 2.80. Remember, that's pOH. We need a pH. This question asks you pH. So 40 minus, that's what is 11.20. And That's it. That's the answer for this question. Look big, small, easy to solve. So since we're doing 6, 7, let's go on to do 8. So this is a pH for this solution. So again, we assume the x is small. And what do we do? We use this formula, the trick we showed in the previous video, negative log. And for this one, we use KB. So 1.8 multiplies 10 to the negative 5 and plus log. And we want its conjugate acid to be on top of 0.32, and we want molarity, and we want its weight base on the bottom 0.25. And that's it. That's your final answer. But this is going to be POH. And we need to use 14 minus the POH. So let's do it. So this can be done in one step. So negative log 1.8 multiplies 10 to the negative 5, and then plus log. And on the numerator, we'll have 0.32, and the denominator will have 0.25, and then the total is 4.85. So that's POH equal to 4.85, and 14 minus 4.85 is 9.15. That's it. That's the final answer for pH for question 8. Okay, question 9. For this question, we'll add acid to this buffer, and acid gonna react with the weak base in the buffer. Weak base gonna buffer the strong acid. So again, we need to know how many bases used for this 0.03 mole strong acid, and that's gonna all turn into, if the buffer successfully ameliorated the pH change that created by this strong hydrochloric acid, then all the mole of the acid will be the mole that, if it's 1-to-1 ratio, stoichiochemistry gonna be all the mole that conjugate base we created. So let's do the mole for our weak base for now. So let's do that. 0.23, let me put my calculator there. 0.23, I don't know if it's clear. Multiplies 0.521, that is 0.12. And we only need a 2 significant number, so 0.12 mole of ammonia. And now let's get the other species, which is conjugate acid over there in the solution, or you can call it a salt in the solution. Let's do 0.24 multiplied 0.521, that is 0.13. So this one gonna be 0.13 mole. And so now we can see very clearly that our buffer was able to get rid of the strong acid and doesn't change the pH much. So we're gonna get rid of a 0.0 mole from the weak base, but gonna add those mole to its conjugate acid. We're gonna create an NH4 chloride. So what's gonna happen is the mole of ammonia gonna drop to 0.09 mole, but the NH4 cation gonna go 0.016 mole. So that's just a new mole over there. And remember, we're in the same solution, so we don't need to calculate their concentration. All we have to do is use that formula. Again, this 9 is closely related to the last video. So we're going to do a log, and remember, we're using our weak base, so it's going to be log KB. We're already given KB, so there's no trick here. We just put a KB over there. And plus, it's a conjugate acid. What is a mole? New mole. 0.16 to divide its new mole for the base, weak base, 0.12. And that's it. This is going to be POH. Then you get a pH by using the 14 minus POH. So let's do it. Just one string, we got it fixed. We got it done. So KB is 0.8. This question has so many 0.8 and KB. All right, I guess whoever have these questions, I kind of twisted this, I kind of added this question a little bit, likes this ammonia KB. So next log plus log 0.16 to divide 0.12. I'm sorry, I made a mistake. Remember the original 0.12, after reckoning the hydrochloric acid, it's gonna be 0.09. Remember, circle this 0.09, right? It's not 0.12, so let's change it, 0.9. And that's it. pOH is 4.99. 4.99. So what our pH is? So it's gonna be 9.01. Okay, that's our pH for question 9. For question 10, since we're question 9, let's do question 10 as well. How many grams? So first of all, we need to know I think it's 59.3 131 something, 131 something. So just to put 59.1 for molar mass. For that, once we get the mole and we have a molar mass, we can get the gram. Okay, so right here is this is a salt, has the same cation that conjugate acid ammonia has. Ammonia gonna create a conjugate acid, so we're gonna add this salt in, create a buffer. So yeah, to produce a buffer solution. So now we are given pH. But do we need a pH? We need a pOH because this is a base. So pOH going to be 14 minus 9.43. It's going to be 4.57. And that's our pOH. I'm going to put it here, pOH. And equal to negative log Kb, or given that Kb. What I'm missing is a log here. And the log, inside the log, we need to know how many moles of our ammonia is, and how many mole our NH4C1 is. So what do? We use X. So we're gonna say X here, and the bottom gonna be let's do a quick calculation for the mole here. So 0.374 multiplied 0.231. That's 0.0864. So 3 sigma number 0.0864 mole. Mole. So again, we can calculate the X. How do we calculate X? So basically, it's 4.5 and minus or plus the log Kb, 4.57. Let's just do some like arrangement. And then you put 10 on the left, and the right is going to be X, and divide that 0.0864. And then you just multiply that, then you can get it. Can you see here? So what I do is this. So we're going to do, let's calculate log Kb first. So I have Kb, we're going to do a log Kb. Log Kb is 1.8 again. -5. That's our log Kb. Log Kb must plus 4.57. That's the pOH. And then we want to 10 to this power. And then after 10 to this power, everything is done in the calculator, so I don't have to write down anything. And we want to multiply the mole of our weak base. Going to be 0.0864. What is the answer? Okay, the answer is 0.0578. I'm going to write down 0.0578 mole of our salt. Or you can call it a conjugate base or a cation of or you can just NH4 plus. But NH4 plus has the same mole our salt has, because salt added the NH4 plus. So, and again, we'll zoom X is very small, and the X is indeed small. So, this X is not that X. This X is the mole of our salt that we add. Okay? I'm talking about the small X. I'm talking about the hydroxide ion that NH3 create in the solution. So that is